All right, so here's our lesson on inverse trig functions. So it's in math, inverse is always going to mean the same thing. So you learned about inverses in Algebra 2. So does anyone remember how we would find the inverse of that function f of x equals 2x minus 4? What was the general strategy for finding an inverse in Algebra 2? Does anyone remember? It's been a while since we've done a live lesson, so I get it. Yeah.
So don't you like put 2x minus 4 into the x spot?
Very good. Very close. Yeah. You're going to switch the x and y, and then pretty much going to switch those two. So you're not going to plug in 2x plus 4 for x, but you're going to replace f of x, which is y, with x, and then replace x with y. So in math, inverse means to switch x and y, and that has a couple consequences to it, and we'll look at it graphically and algebraically. But yeah, if I wanted to find this inverse, I'm going to replace f of x with x and x with y, and then solve. So I'll add 4 to both sides, and then divide by 2, and I get that's what y is. So that's my inverse. So f to the negative 1 of x, whenever you see that negative 1 exponent for like a function, it means the inverse of the original function. So since we switched x and y, that means if I were to take f and let's say plug in 1 and get a y value, so 2 times 1 is 2 minus 4 is negative 2. That means if I take the inverse of f and I plug in negative 2, without even evaluating this, I know it's going to equal 1. And if you don't believe me, you could plug in negative 2 and see that it simplifies to 1. Negative 2 plus 4 is 2, divided by 2 is 1. So that's what it means to be an inverse. X and y just switch. So there's the x of the original function. There's the y of the inverse. Here's the y of the original function. That goes with the x of the inverse. So when you see inverse in math, just think switch x and y. Now, graphically, does anyone remember from geometry what the, does anyone remember from geometry when you, what was the, this is a tough question, not that tough, you'll be able to get it, but when you did transformations, if I wanted to take a point, let's say the point was 4, 2, and then I switched x and y. So now it's 2, 4. Does anyone remember what transformation that was? So, you know, was it a rotation, 90 degrees? Was it a reflection over the x-axis? It wasn't either of those two, but that's what I'm looking for. When you switched x and y, what type of transformation occurred, like graphically?
It kind of looks like if you had just like fx, just like normal x, like the diagonal.
Yeah.
It's like on the opposite side of that.
Very good. Brigitte, is that what you were going to say? Yeah. It's a, no, you're good. It's a reflection over the line y equals x. So when you change x and y, so like when x comma y becomes y comma x, so you switch x and y, that's going to be a reflection over the line y equals x. So if we take a whole function and switch x and y, it's going to be a reflection over y equals x. Let me show you. If I go open up like a Desmos, all right, and I type in any function, let's say I'll type in y equals x squared minus 3. Now let's go plus 2. Now if I type in the same function but replace x with y and y with x, all right, the red graph got reflected over the line y equals x to get the blue graph. And that's mainly going to happen with sine, cosine, and tangent, just one extra caveat, and we'll see that. So some notes about inverses, and feel free to write this down, like just jot down like notes, but you have these notes for you, so I'm not going to give you time to like write down every single word, but you can reference these later. But so notes about inverses: a function and its inverse are symmetrical over the line y equals x. All right, that's what we just talked about. The x and y values are switched. All right, that's what it means to be an inverse. You switch x and y. If a function passes the horizontal line test, then the inverse exists, meaning the inverse is a function. So if we think back to that parabola I just showed you, it didn't pass the horizontal line test, because if I drew a horizontal line through that first upward facing parabola, it would have crossed it at 2 points, which means when you switch x and y, the new function or the inverse isn't going to be a function, because that's going to fail the vertical line test. And I'll show you again what I mean when I pull up the graph. For inverse trig functions, the graphs must contain the origin. This is called the principal branch of the graph. So we're going to have to take sine inverse, cosine inverse, and tangent inverse and limit it to certain values. So when we limit it, we want to make sure we include the origin, mainly because it goes on forever in both directions. So the origin, like 0, 0, is just like a nice place to start. All right, that's called the principal branch of the graph. That's a term I've never heard before until I opened up these notes. So don't worry about memorizing too much, but that's a good fun fact. All right, but just back to this Desmos here, this graph I did. Notice how the red graph does not pass the vertical line test, right? If I draw a vertical line through it, it hits it at 2 points, which means when I switch x and y, sorry, that's a horizontal line. I could draw a vertical line through x equals y squared plus 2, and it crosses it at 2 points, which means this blue graph is not a function. So if your function fails the horizontal line test, that means the inverse is not a function. And we like things to be functions because when we plug in the x value, we want to get exactly one y value. Yeah, sure. All right, so now we're only going to graph y equals the sine inverse of x, y equals the cosine inverse of x, y equals the tangent inverse of x. So when you're graphing these, you don't have to worry about like period and increment and starting point. We're only going to graph like those 3 basic ones. When we graph the inverse trig functions, we do it to understand their domain, range, and restrictions. So we're only going to do that like now so that you understand why we restrict it, and then you really won't have to graph it much. This will help us in evaluating inverse functions. So a little note on notation. So some calculators, like on the TI Inspire, you might see y equals the sine inverse of x. But other calculators, you might see a button called arc sine of x. It's just notation. It means the same thing. So cosine inverse is the same thing as arc cosine. Y equals tangent inverse is the same thing as arc tan. And on a TI Inspire, that's probably the more common calculator used in this class. If you open up a new calculator and you go to trig, all the inverse functions are right below their original function. All right, so they're right there. And if they're locked for you, that means you're in test mode, and let me know and I'll take you out of test mode. All right, so graphing the sine inverse of x. That's how we call it. When you see the sine to -1, we call it the sine inverse of x. First, we're going to graph y equals the sine of x. So there it is. All right, we got a period of 2 pi. That's 2 periods. We start in the middle. So We got a point on the sinusoidal axis. Then we go to the high point, middle, low, and then back to where we started. All right, so that's one period of sine. And then you could go in the other direction and get 2 periods. Since it's the sine of x, the amplitude is 1. Since we're not adding anything to the end, the sinusoidal axis is 0. And since the period is 2 pi, because b is 1, the increment is pi over 2. So that's why we plot a point every pi over 2. Okay, so, yeah. Yeah, we didn't graph the inverse yet. So all we're going to do now is we're going to take those points and switch x and y. And we're going to see that it gets reflected over the, not the x-axis, close, the line y equals x. So it's going to be reflected over this line here. Now you have to keep in mind that pi over 2 is greater than 1. So like 1 on the x-axis is around right here. So the line y equals x will have a slope of 1. Like it'll look something like that. So we're going to take this sine of x and reflect it over this green line, which is the line y equals x. And we're going to see it's going to be like a squiggly line going like up and down. So you'll see it in the next slide. All right, so for inverse trig functions, the graph must contain the origin. This is called the principal branch of the graph. So if we take this graph and just switch x and y, so let's look at a couple points that we could plot. We're going to plot the point 0, 0. Right? If you switch x and y, it's still going to be 0, 0. We could plot the point pi over 2 comma 1, but we have to switch x and y. So we're going to plot the point 1 comma pi over 2. Or switch x and y, negative 1 comma pi over 2. Or 0 comma pi. Or negative 1 comma 3 pi over 2. So we could take these like big points that are like on nice y coordinates. So this point is 2 pi comma 0, and then switch x and y and get 0 comma 2 pi. And if we do that, we see that the graph will look like that. All right, so it's got reflected over line y equals x. So that's what it looks like. So if we switched every x and y value, this is what the relation would look like. But what's wrong with this picture? If you graph something like this in algebra 2, do you notice anything that's a little different about this graph? Yeah, it's vertical. You don't see a lot of graphs that like fold over themselves vertically. So it fails the vertical line test. If I graph a vertical line, it's going to hit this at more than one point. All right, and that's not okay because then it's not a function. All right, and I'll explain what I mean. All right, so if I was doing what's the sine of 30 degrees, all right, it's going to give me one answer. It gives me 1/2. If I do what's the sine of 150 degrees, I'm going to get one answer. It's going to be 1/2. If I do the sine of 390 degrees, I get 1/2. All right, I'm getting repeated y values, but that's okay. For it to be a function, if you plug in an angle, you should get exactly one ratio. All right. Now, if I do the inverse, so now if I did the sine inverse, so I'll write arc sine because I don't know how to do exponents on Zoom. So arc sine of 1/2. Well, right now it could be 30 or 150 or 390, or there's an infinite amount of angles it could equal. That's not good. It's not a function then, all right? So we want to restrict the domain of arc sine so that we only get one answer. like 30, the one closer to the origin. So that's exactly what we're going to do. We're going to cut off this graph so that it is a function. We're just going to take the part of the graph that'll make it a function and try to take as much as possible. So how do you think we should? So I'll keep this picture up. What y values should we restrict this graph to so that if we just limit it to those two y values, it would still be a function, so that it would still pass the vertical line test? There's actually many correct answers, but there's only one that we're going to use.
You're saying like to fix the graph so that it passes the vertical line.
Yeah, so like I'll give you a hint. Like if I yeah, but look on the y-axis. Like if we cut off the graph, so let's say, I need to get my thing here. Let's say we just cut off like this part and this part, and we just worked in between those two parts. All right, on that interval, it's a function because like on that interval, like it passes the vertical line test. So I'm asking like, what would be the best two places to cut it so that it's a function? And I have someone who sent the chat. Pi over 2, I like that. So if we cut off at pi over 2, we're on our way to making it a function. But right now, if we don't cut it somewhere else, it's going to fail the vertical line test, like going below pi over 2. So where else should we cut it?
Are you drawing the line down from like where you cut it and above?
Well, this vertical line is just the vertical line test. I'm showing that like it hits the graph at 2 points, so it fails the vertical line test.
Even if you cut it pi over 2?
Yeah, if you go below it, you have to cut it somewhere else. And so that's just like one section, so that's not going down forever. And negative pi over 2, so let's try it. So yeah, if we cut it between pi over 2 and negative pi over 2, all right, and so I'm going to block out this part, block that out, and we'll block that out. All right, if we just look on this interval here, now it's a function. It passes the vertical line test. All right, if I limit the range between pi over 2 and negative pi over 2, now if I say, what's the arc sine of 1/2, all right, there's only one angle that you could take the sine of to get 1/2 that's on that interval, and it's 30 degrees, which is pi over 6. If you tried like 150, that's 5 pi over 6. That's going to be like somewhere up here, but it's outside of the range. So you want to restrict arc sine or sine inverse, cosine inverse, tangent inverse, so that it's limited to a part of the graph where it's always increasing or always decreasing, where it's not like folding back onto itself and it'll fail the vertical line test. So on this interval, it's always moving to the right and up. Once you go past it, then it fails the vertical line test. So that's why we limit it between pi over 2 and negative pi over 2. That's all you really need to know from this. This is more explaining like why we do it. All right, so this is what it should look like. So these are the graphs of y equals the sine of x and y equals negative the sine of x. So it's kind of weird. This one here is the one for, I spotlight it. It's not a spotlight. Sorry, I'm learning this. Spotlight. Here we go. So like this graph here looks weird because notice how the y-axis is in like pi over 2, and negative pi over 2. Normally our y-axis is going to be like 1 and negative 1. If we take those points, switch x and y, that's all this sine inverse is going to look like this part right here. All right, so that's y equals the sine inverse of x. You get the graph, by graphing y equals the sine of x, switching x and y, but then limiting your range between pi over 2 and negative pi over 2. And you could think of that as quadrants 1 and 4. And if we draw out the like all students take calculus thing, we could see another reason why it makes sense to restrict it to quadrants 1 and 4. So if we're talking about sine, all right, so all students take calculus. So draw, if we look at sine, sine is positive in quadrant 1 and negative in quadrant 2. It's positive, sorry, quadrant 4. It's positive in quadrant 2, negative in quadrant 3. So if you think of it as this, that in quadrants 1 and 4, we're going to hit every possible value for sine. In this quadrant, we get all the positive values for sine. Here we get all the negative values for sine. Once we go into quadrants 2 and 3, we start repeating those ratios. Like the sine of 30 is 1/2. The sine of 150 is also 1/2. So we're repeating 1/2. So that's why for sine inverse, we restricted quadrants 1 and 4, or in degrees between 90 and negative 90. So sine inverse can only equal angles between 90 degrees and negative 90 degrees, or in radians, pi over 2 and negative pi over 2. Now we're going to do the same thing with cosine and tangent. Cosine's a little different because what happens if I truncate it, big word, watch. If I cut the graph between pi over 2 and negative pi over 2, what's the issue there if I were to change x and y and only use that interval? Got tape on my nose. I was trying to tape my mask down, but it didn't work. But I did clear my pores, so that's good. True. That's very true. You don't get any negatives. I wasn't thinking that, but that's a very true statement and one reason why we can't do it. So how do you tell if a function's inverse is a function? What's the test for that? We could test something as a function by doing the vertical line test, but if we want to see if the inverse is a function, we do the horizontal line test. And if we look at this interval here, it fails the horizontal line test, which means when we switch x and y, it's not going to be a function. So what would be a better interval, like between what two x values should we cut this graph off? And maybe it'll make more sense if I show you what it looks like after we switch x and y. All right, never mind. So where should we restrict the graph so that it passes the horizontal line test? Because if it passes the horizontal line test when we switch x and y, that'll pass the vertical line test. And you might not be able to see this. So like that's 0, pi over 2, pi, 3 pi over 2, 2 pi. I think that's a good idea. Let's try it. So from 0 to pi, if we just use that interval, that's going to pass the horizontal line test because it's always decreasing. It's not decreasing and turning back up like our parabola. So for cosine, we want to restrict that to 0 and pi. So cosine inverse could only equal angles between 0 and pi.
So like if they ask, if you ask that, you write the domain as the answer.
So you'll see, you're going to just, so it's, yeah, so we're going to restrict the domain of cosine to be between 0 and pi, which means when we find the inverse and switch all our x and y's, the range for cosine inverse is going to be between 0 and pi. The domain for cosine inverse is going to be the same thing as the range for cosine. So the range for cosine goes from 1 to -1. So that just means the domain for cosine inverse will be between 1 and -1. All right, so same thing with sine. For sine inverse, that domain is the same as the range for sine. So it's always like, when in doubt, just think switch x and y. If you know something for sine, just switch domain and range, and it'll be the same thing for sine inverse. The only caveat, the only difference is for sine, you restrict it, the range of sine inverse between pi over 2 and -pi over 2. For cosine inverse, you restrict it to 0 and pi. So that's gonna, so this bottom graph here, if I get my spotlight going. Nope, that's not a spotlight. That's not, I wonder what it looks like at home because it doesn't do anything for me. But this graph here would be cosine, and then you reflect it over this line, y equals x, and you get cosine inverse. All right, so cosine inverse is going to have a domain of 1 to -1 because that's the range of cosine. And the range of cosine inverse is going to be limited to 0 to pi. Because the range of cosine inverse should be the same thing as the domain of cosine, but cosine has a domain of all real numbers. You can plug in any number for cosine and get a ratio. You have to restrict it. And it's restricted to quadrants 1 and 2. And if I make another little picture here with the all students take calculus thing, for cosine, A, S, T, C. So like Brigitte was saying, in quadrants 1 and 4, cosine is positive. So if we were to restrict it between pi over 2 and -pi over 2, we would only be getting the positive values. So that's why we use quadrants 1 and 2 for cosine, because sine is positive in quadrant 1 and negative in quadrant 2. Oh, and I used all the colors for the flavor rainbow sherbet. I gotta get some rainbow sherbet. Great ice cream, underrated. Doesn't get enough love. We got the green, the purple, and the orange. Fun fact. All right, so cosine inverse, all that stuff I just talked about, the main takeaway is that cosine inverse can only equal angles in quadrants 1 and 2. So between 0 and pi. Okay, then tangent is going to work just like sine. Right? Tangent, if you look at it, where's some nice point? I gave it away right at the beginning, but maybe you didn't hear me. What would be a nice place to restrict the graph for tangent so that it passes the horizontal line test? So that means if it passes horizontal line test, when we change x and y, that'll pass the vertical line test. So in case you can't see it, that's 0, that's pi over 2, that's pi, -pi over 2, -pi.
You break it off at pi over 2 and -pi over 2?
I like it. Let's try it. Yeah, so if we break it off here and here, if we only look at that interval, it passes the horizontal line test. If we didn't restrict it, then see, it wouldn't pass the horizontal line test. But if we only look between pi over 2 and -pi over 2, it does. Very good. Which means that the inverse is going to look like that. And it is kind of weird to graph. So if you had to graph it, all I would say is take your 3 nice points. Like take the point 0, 0, the point pi over 4, comma 1, the point -pi over 4, comma -1. Take those 3 nice easy points, low, middle, high, and then switch x and y. You can even take your asymptotes. You could take this asymptote at x equals pi over 2 and x equals negative pi over 2. And then take all 5 of those points and asymptotes and just switch x and y. So instead of graphing x equals negative pi over 2, like graph like y equals negative pi over 2. Instead of graphing, and do the same thing with negative pi over 2. And then take these points and switch x and y. So like it would be like over here and like over there. They're pretty close to the line. And it would look something like this. My drawing's not very good. I look like I am a murderer. But if you look at this picture, it comes out a lot nicer. All right. So since tangent of x has a range of all real numbers because it goes up forever and down forever, see that? The domain of tan inverse is going to be all real numbers as well. So that means you could plug in any ratio for tangent inverse and you'll get an angle. The range is going to be restricted to quadrants 1 and 4, just like sine. So here's all the important info. I would definitely take a moment and write that down. Right, then we'll do some practice problems together and we'll call it a day. We'll call it a Doug a day. Any questions? I must say that was way more fun for me than sitting here grading your stuff on Google Classroom all period. I think I'll just give less assignments and do more of this. I think it's better for everyone. All right, so you can find this on Google Classroom. I'm just giving everyone like a minute or two to write it in their own notes, and then we'll do like 10 minutes of practice. And then we'll do this more next class, which I think is tomorrow. I'm not sure. Maybe not. Maybe Monday. Yeah, Monday. Yeah, baby. Friday. All right, anyone need more time to jot that stuff down? Nope. You can find it on Google Classroom. So let's do some practice. So yeah, we'll do these now and hopefully you get them done, submit that, and you'll get 2 points for the homework. So evaluate the expression without a calculator. Let me zoom in a little bit. So write your answer in radians. Now it helps if you have a unit circle in front of you. So if I have to pull one up, I will. But the way you're gonna do these is just literally switch X and Y. So this equals something, and we're trying to find that out. So the definition of inverse means you could switch X and Y. So if the tan inverse of 1 equals X, that means we're trying to figure out the tangent of what equals 1. So what angle do we take the tangent of to get 1? And there's actually an infinite amount of answers. So just give me one of them. 45. Very good. So if you have your table memorized, you know the tangent of 45 is 1, which means the tan inverse of 1 is equal to 45. So X is equal to 45. Now you have to make sure that it's in the range of tan inverse. And it is, because tan inverse has to be between 90 and negative 90. So that works. So our answer is going to be pi over 4, because we want to put it as a radian. So pretty much you're looking for these angles, but they have to be in quadrants 1 or 4 for tan and sine, and 1 and 2 for cosine. And when I say quadrants 1 or 4 for tangent and cosine, tangent and sine, they have to be in between 90 and negative 90. So if you got something like 330 degrees, you would want to write that as negative 30, not 330, because 330 isn't in the range. All right. I'll save B. I'll let you do B. Well, let's do an arc sine. And actually, let's do D. So for D, we're thinking, okay, what angle do we take the sine of to get negative root 3 over 2? So in our heads, we're thinking of the sine of what is equal to negative root 3 over 2. Okay, I got a chat, boy. So I would think of the reference angle first. I wouldn't even worry about the negative. So like the sine of what angle is root 3 over 2? $60, very good. So it's negative root 3 over 2. So this is going to be negative 60. That's it. Because we could say it's 300 degrees, but that wouldn't be in between 90 and negative 90. So our answer is going to be negative 60, which as a radian is going to be negative pi over 3. All right, now cosine inverse is going to work very similarly, but if we get a negative ratio, we're not going to use quadrant 4. We're going to use quadrant 2. So cosine inverse can only equal angles in between pi and 0. So between 0 and 180. So if I was doing this, I would think to myself, all right, the cosine of what angle is equal to negative pi over 3? At first, I wouldn't even worry about the negative. I would just think, all right, the cosine of what angle is positive pi over 3? Sorry, root 3 over 2. My apologies. The cosine of what angle equals positive root 3 over 2? All right, that'd be 30 degrees. So the cosine of 30 is equal to root 3 over 2, which means our answer has to have a reference angle of 30. and it has to be in quadrant 2. So if we draw a 30-degree angle in quadrant 2, oops. That's going to end up being 150 degrees. Yo.
I just got out of class and she leaving, so
Yeah, well, after this one, we'll let everyone go. So 150, and so just convert it to radians, so it'd be 5 pi over 6. All right. So that's the last thing I wanted to show you was if you're doing it with a calculator, you can literally just type it in the calculator, but just realize that it's only going to give you angles in the respective quadrant. So like this will give you an angle in quadrant 1. This will give you an angle in quadrant 2. This will be quadrant 4. This will be quadrant 1. All right, so we got like 9 minutes left. If you need to go, you're free to leave. If you want to stay and ask questions, I'll stay until the last person goes. And so finish this for homework, submit it. Hopefully you can finish in like 10 minutes. And then we have another assignment of inverses on Monday. All right?
Thank you.
Thank you.
Thank you.
Thank you.
Thank